Let's get started. Yeah, so today's weird. So thanks for joining me. I need to be here because the lectern automatically records it. So this is how I can get the recording. All right, yeah, so electron one. Ignore the correct answer. I don't know. It makes me pick a correct answer. I don't know what it does. But yeah, you guys picked electron. And I just mentioned before that if I got a vanity plate for like a new car, it would say electron. So if you see an electron zipping around the highway, though I drive pretty slow, so I wouldn't be zipping around, it'll be electron, all right? Okay, and I wanted to just announce that I've reopened all of those Carmen practice exams, because I think before it was like one attempt only, but I opened it back up, all of them, so even the final, so you can take it multiple times. And do remember that all of those practice exams have video feedback made by Dr. Foos for those, so there you go. Okay, so what do we want to do? We left off, we're just doing midterm practice, so oh, nope, that's for the end. I was going to do a demo, but we can't do the demo. I'll just talk about my tractor instead. Okay, all right, okay. All right, so we talked about chapter 12, solids, right? We looked at this idea of identifying the type of solid that something is based upon a description. And so we looked at this question, and I think the big idea here is that ionic solids, even though it's ionic, when they're in the solid phase, they don't conduct electricity until you either dissolve it in water and so forth. So do know some, defining characteristics of some of these things, and we talked about that. So molecular solids, they typically are soft or have low melting points. Let me define what I mean by low. I would say a low melting point is something that's less than 500 degrees Celsius. I would say that's low. So if you have a solid that has a melting point of 100 and 150 degrees Celsius, it's probably a molecular solid. But if it's something on the order of 800 degrees Celsius, then you're probably getting into ionic solid range. And then when it has a really, really crazy high melting point, 1800, then you're probably either on the high end of ionic solid or even a covalent network solid. All right, so what I mean by low is about 500. Good? All right. Okay, so let's do some other ones. Okay, how about these pictures? Okay, so these are other depictions of solids. These are alloys. So, you can think about packing pure, the same atom over and over and over in a crystal structure, and that is a pure substance. But we can also have alloys where we have different elements present. So a lot of the metals that we work with on an industrial scale as humans are actually alloys, because the pure metals typically don't have the right characteristics that we want. So we oftentimes mix metals with other metals to get the right things that we want, corrosion, anti-corrosion properties, strength, things like that. So stainless steel, those things are all alloys. So based upon these crystal structures, we can get structures of different alloys. So alloy A, B, and C. And so we talked about 3 different alloys: substitutional, okay, heterogeneous is not an alloy, substitutional, interstitial, and what's the last one? Intermetallic. Those are the 3 types. What do we think these are? I feel like it's by the name you can tell what it is. A is what type of alloy? You can see the colors, like the light atom. How does the light atom put itself into the crystal structure? Yeah, it's literally substituting other alloys, so A is substitutional. All right. Then B, so the little carbon atom here, would be, is what type of alloy? It is inserting itself into the crystal, or it's inserting itself into the voids of your crystal structure. So alloy B would be interstitial. Do you see that? All right, and then the last one here is a little bit different. The last one is called intermetallic. and it's one that has a very defined crystal structure or atom ratio. Within our substitutional alloy, you can see that the added metal is kind of put in randomly on a particulate level, but in an intermetallic compound, you have a very, very ordered ratio of certain atoms. It's so ordered that you can express your metal as a chemical formula, typically. And so that's how you can identify it based upon formula, if you're given something, if it's intermetallic. So I guess what's the answer? A? Is it? Wait. B. Okay, good. Yeah. All right. Yay. All right. Yes, what's up? Yeah, coordination number is, you look, typically this is done with ionic compounds, all right, where you look at the cation and you count how many adjacent anions are touching it. And so that's the coordination number of that cation. So let me look, do I have an example? Okay, yeah, so right here. This one's kind of hard to see. Okay, let me delete this. So this one's hard to see. Do I have another picture? No, I don't. No, I don't. So how you would go about this is you would look at one of the ions, so like the red atom, and you would count, okay, how many adjacent blue atoms are around it? And this one's kind of hard to see because it's a more complex crystal structure, but let me draw one instead. So I have my unit cell. Okay, so there's a cube. Okay, so I have two different atoms. Let's say I have like a red atom, that's my, I don't know, anion or something. And then I have a pink cation in the middle. It's in the straight middle of your unit cell. So if you are the cation in the middle and you look around and count how many anions are adjacent to you, there would be 8. Do you see that? So this cation has a coordination number of 8. Oh, okay, yeah, all right. So you said, okay, so the cation has a coordination number of, well, I'll just make it number 6, okay? So in order for the unit cell to be balanced, let's pretend that the formula that we're talking about is AB, meaning there is one A cation for every B anion. So if there are 6 anions surrounding every cation, has a coordination number of 6. In order for the formula unit to be balanced, for there be to a 1-to-1 ratio of cations to anions, what would the coordination number around your anions have to be in order for you to have a 1-to-1 ratio? So if every cation, yeah, it's actually 6. So you kind of take the ratio and simplify it. All right, so every anion needs to have 6 cations around it in order for you to get an AB type formula. But let's pretend we had AB2. So this means there is twice as many anions, right? So if I have a coordination number for my A as, let's say, 6, so A, what that means is that there are 6 B atoms around every A atom. So if I'm trying to figure out the coordination number around B, 3. Yes, it has to be 3. That if you are a B atom, there's half as many A atoms around you. Does that make sense? Yes. Yes. So you look at the ratio, but you kind of have to flip it a little bit. Right? Because it's like 6-to-3 for A, the coordination A to B, but it's A, B2. Yeah, okay. Yeah, I just like to think, oh, there's twice as many B atoms in your unit cell, right? Okay. All right, so then if it was your question, if it was AB3, then B would have to be 2, yeah. Wait, A to what? B3? Oh, geez. Would it be 4? Would it be 4? Wait. B9? Okay, this is a little too complex. Let's just, it's a little bit, I don't think that'll be asked. All right. It is? Oh, is it on the homework? Okay, so let's do the same idea here. Okay, so if every A atom sees 6 different B atoms, that means, okay, so usually it's you take the ratio, but you have to flip it. Oh yeah, it would be 9. So that means, wait, would it be? Or is it the other way? No, it's the other way. It would be 4. It'd be 4. So every A atom sees 6 different B atoms. And so B, since there are less A atoms, would only see 4 other A atoms because there's less of them. Yes. So I usually simplify the ratio and then flip the subscripts. So the coordination number is, you simplify the coordination numbers to like the lowest common multiple, and then you flip the coordination numbers to as your subscripts in your formula unit. I don't know how you got 9. Yeah. So are you not getting the right answer either? Or? Yeah. Yes. So let me just go back to this example. Right? So if A sees 6 B atoms, there's twice as many B atoms. So B, there's only 3 of them. Right? So I divide both by 3, so you get 2 to 1, but then you switch it. Yeah. Oh, is it 4? Oh, I'm sorry. So that's just one homework question. I'm sorry about, is it multi-part? Yeah, that's probably why there's just one weird one. I'm sorry that I led you astray. But I want us to continue here on other questions, okay, not just homework questions. Okay, all right. Ones that can get us bigger impact on the final. Okay, so sorry about that. I looked at it. I think it's fair. 53. No, that's okay. All right. Okay. So amongst these phase transitions, melting, vaporization, sublimation, freezing, condensations, which ones are exothermic? So this is a little bit of chapter 5 thermochemistry that you asked about. So exothermic, we need to think about means what? It's a process that releases energy, yes. Its delta H is a negative value, so it means that it releases energy. So I like to think that your system becomes more stable. Because if you go from a higher energy state to a lower energy state, then energy has to be released. That's exothermic. Heat is given off. So I like to think, okay, all of these different phase transitions are between what different phases, and I just kind of think, okay, it goes gas, liquid, solid. Which ones go down in energy, essentially? Because I can't, sometimes when I think of melting, I have to think for a second about what phases that's between. Melting is what, solid to liquid? So is that a positive or negative energy value? Positive, okay, good. Vaporization, that is a liquid to a gas. So that is what type of energy? Positive. Sublimation is a solid to a gas, is that right? Yeah. So that is positive again. Yeah. Think solid, you know, the particles aren't moving that much. Gases, they're off the walls. All right, freezing is liquid to solid. So that one would be negative because you're going from higher energy liquid to lower energy solid. Condensation, liquid to, no, gas to liquid, yeah, gas to liquid. So that's negative, and yeah, so it's just those two. So freezing and condensation. So me, personally, I can't just look at these words and know. I have to actually think about what chemical transition, what physical transition are you doing to figure out the sign. It's not super intuitive to me. Okay, so let's keep going. Let's go backwards. All right, which of the following substances, arrange them in increasing boiling point? So I want you to be able to think quick on your feet. So when you see a word like boiling point, what property are we looking at? IMFs, intermolecular forces. So hopefully if that can save you time on the final, just recognize like if you see a question about boiling point or even viscosity or something like that, then that means you need to be looking at intermolecular forces. Okay, so then we just look at the intermolecular forces present in all these things. All right, okay, I guess what's the trend? If increasing boiling point, we typically see an increase or decrease in IMFs? Increase, yeah. More attractions, higher boiling point temperature. So going through these, I just identify what is the strongest intermolecular force, the strongest one, and then that will allow you to order things. So this silicon compound, if you draw out its Lewis structure, it looks like CH4. It's nonpolar, so all it has is LDF. That's it. So how I got that without like actually drawing it out is that I just see silicon as group 4. It typically makes 4 bonds. There's 4 hydrogens there. So I can get that without actually drawing the Lewis structure, yeah. Yes, only if all of the bonded atoms are the same. Yeah, so if I have CH4, yes, that's nonpolar. But if I have CH2Cl2, that's still tetrahedral, but that is polar. Yes, so yeah. But if I had CCl4, that is nonpolar. Okay, all right. Okay, that has LDF. Here, this alcohol has 2 alcohol groups. Yeah, do you see it? It has 2 sources of hydrogen bonding, 2 H bonding. You see that? And then water also has 2 sources of H bonding. So that's something else. But of these 2, which one has more overall intermolecular forces? Water or that ethanol? Or this one, because it's both heavier and it has 2 hydrogen bonding. So this one has the most intermolecular forces present. And then H2S. This one's always a tricky one because folks will think, oh, it looks like water, it has to hydrogen bond too. But sulfur cannot hydrogen bond. It can only do dipole-dipole. So if we arrange these from lowest to highest, it should be silicon, that silicon compound. Next, it's the sulfur compound, then it's water, and then it's the alcohol thing. Okay, we see that? Okay, and I don't know what answer that is. E? Is it E? I don't know. Yes, that's what my key says. Okay, cool. All right, let's just keep going backwards. Unless someone tells me a page number that they want to do specifically. Okay. All right, given the following boiling point data, which of the liquids would you expect to have the highest vapor pressure at room temperature? So again, like boiling point, automatically relate this to IMFs. When you see something about vapor pressure, or something about boiling point, it's related to intermolecular forces in your sample. So as intermolecular forces go up, vapor pressure trends how? It decreases. I like to think of it as intermolecular forces are really strong in your liquid. So your particles, they're all hugging each other, they're all attracted to one another, so that means they're not going to let go of any particles going to the gas phase. So you typically won't have any of those gaseous particles like enter your nose, so we typically think of those compounds as not very smelly. That's how I like to think of it. All right, and so something about vapor pressure is that We can increase, so note that this question says at room temperature, that we have to measure all of these samples at like one consistent temperature. Because if you change the temperature of your sample, vapor pressure changes, right? How does that trend? As temperature goes up on your sample, vapor pressure decreases? Increases. Yeah, the hotter things are, the smellier they are. Yeah? Yes. But the thing is as you heat your liquid, will the vapor pressure continue to go up infinitely? No. It'll stop. Your vapor pressure will stop at what pressure on Earth? 1 atm, yes. Once your vapor pressure of any sample is 1 atm, whatever temperature that is, your sample will boil. Does that make sense? Yes. So that's why if you think about these, like if you have a sample that has high intermolecular forces, like ethylene glycol, all right, that it has a very low, what are we doing? That have the highest vapor pressure. So ethylene glycol is going to have the lowest vapor pressure at room temperature. So that means you have to heat it a lot to get it to a vapor pressure of 760 torr. That's why it has such a high boiling point. So it's kind of starting behind in the race to boil or whatever, versus which one has the highest vapor pressure? Yeah, ether has the highest vapor pressure. Ether, it smells really bad. All right, it smells so bad that there's so many gas particles in the air when you have a liquid. If you're smelling or wafting a liquid, it's like there's so much vapor that it's basically already boiling pretty much already. That's why it's really smelly. All right, yeah, so ether will have the highest vapor pressure within there, okay? And so here, one thing that they didn't mention here, so, so normal boiling point, what does that mean? Yeah, assuming 1 atm. So boiling point, remember, since we are all humans and selfish, that when we measure boiling points, it's on our Earth. So if you took these samples anywhere else that has a different pressure, these temperature readings of when the sample would boil would be a little bit different. So whenever you see normal melting point or normal boiling point, it's assuming that the pressure is 1 atm, but that's pretty normal since that's where we do chemistry on Earth. But where it can get a little bit iffy is if you go into industries that work with really high pressure systems. That's when things change, right? That water won't boil if you're under high pressure, working with like really intense machinery or something like that. Water is going to behave differently. And so that's where you fall back on your chemistry knowledge and think about that, and you remember me. All right. So let's keep going. All right. Do we need to do gases stuff? Do we want to? Let's just walk through this. Walk through it. I don't want to crunch the numbers. So we have a hot air balloon containing 31,000 liters of hydrogen reacting with hydrochloric acid. How many kilograms of iron is needed to produce this volume of H2? So to me, okay, we are given an amount of H2, but we're given a chemical reaction. So can I use like a liter amount in a balanced chemical reaction? No, we have to be in the unit of moles. So they give us H2, they want us to figure out, okay, how much iron do we need? So I want you to think about chapter 3 where we just did basic, stoichiometry. So based upon this reaction, for every 1 mole of iron that's consumed, you'll get 1 mole of hydrogen. But they don't give us a gram amount of hydrogen. And in chapter 3, we just use molar masses, to convert from grams to moles. But now we're given liters. So is there a certain equation that we can relate liters and moles of a gas? Pivner, yes. So we're just adding this new way to get on the bus to use moles and the stoichiometric ratios. So we are given volume, right? We are given temperature, we're given pressure. So do you see that all we have to do is calculate for N here? So we just plug in all those numbers. We get an N amount of H2. And then we use the 1-to-1 ratio. So thank goodness it's just 1-to-1. But if it were different, right, you would use a different ratio. And then we would get to kilograms of iron. So we get to moles of H2, get to moles of iron, and then get to grams of iron using the molar mass of iron. Yeah. The pressure is not given, but, oh, I thought I changed this question. No, yeah, it's assumed it's 1 atm. Yeah. I thought I changed this question. Just know that on exams it will be much more explicit. This is a badly written question. I took these questions from old exams. Okay, I just copied and pasted them. So sorry about that. Yeah, so we're just going to assume that's 1 atm right there. Okay. Yes. You tell me. What does the question ask? Yeah. Yes. What? So the question was, can we use the relationship 1 mole of any gas equals 22.4 liters? Where does that number come from? Oh, you know? Perfect. Yes, that's at STP. But so when we're at STP, how do you get this number? How do you get this number? You're actually just using PivNert. You're just using PivNert. All right, so at STP, that means 0 degrees Celsius, and it means 1 atm, right? So if you just seriously, just do it. Just plug it in and prove it to yourself. When you plug in those values, okay, 1 atm and calculate for volume. When we try to calculate for this 22.4, what are we plugging in for N? 1 mole, because you just made the relationship that 1 mole of any gas is 22.4 liters. So you are plugging in 1 mole for N. You know temperature at 0 degrees Celsius, and if you calculate volume, you get 22.4 liters. So that's where that relationship comes from, and it's only true at STP. Yeah. Could you plug into... I wouldn't do that. I would just continue to use our whole processes of, okay, figure out how many moles of H2 gas you're given. Then you're saying if iron was like a 2 like this, I would then do a separate step to do stoichiometry to convert it. I wouldn't, like, that's an easy step. It shouldn't be skipped because it's very likely that you could get it in the wrong direction, and then move on like you would normally. Yeah. Yeah. Okay. Yes? You didn't get an option? Okay. So PV equals nRT, nRT. So I plugged in 1 atm, this number, 3.1 times 10 to the 4 liters equals sulfur N, R, and 295 K. And I get that N equals 1,280 moles. Did you get that? Okay. And then I multiply by 1, and then I multiply, what molar mass did you use? Yeah, 55 something, 55.85, and then times, remember we want this to be in kilograms. So 1,000 grams is 1 kilogram. And I got 71. They round, so I actually got 71.5, which would round up to 72, but I circled 71. Okay, well, okay, why don't you just check yourself if you assume 22 degrees Celsius and 1 atm as your pressure, plug that into the PivNert equation with 1 mole of as your N, and you'll get the molar volume, and you'll see it's close to 22.4. So yeah, these conditions are really close to STP, just minus the temperature. So that's why your answer is close. But you know, if we deviate too much from standard conditions, then it'll be way off. Okay. Yes. All right. Good? All right, so let's keep going. All right. For an ideal gas at standard temperature and pressure, STP, we know that. Which of the following properties does not depend on the identity of the gas? The root mean square speed of a gas molecule. Do we even know where to start? So for me, I would think about what is the root mean squared, what is the equation for that measurement? So 3RT over molar mass. So then you ask yourself, does the value that comes out of that equation, does it matter what the substance is? Why? Molar mass, yes, so that's the thing. If there is a molar mass unit within the equation, then it's absolutely going to matter what that thing is. Okay, so A does depend on molar mass, so that's not correct, right? Yeah? Yeah, okay, all right, next one. Density of the gas. Definitely, yeah, it depends, because remember how we calculated density? We assumed that we had 1 mole of gas, where density is mass over volume, and we got the mass of your sample by using molar mass. So again, there's molar mass again. So since we have to use molar mass, that is dependent on its identity. B also depends on molar mass. Or sorry, the identity of your thing. Okay, all right. The average kinetic energy of gas molecules. So was there a relationship that I talked about concerning average kinetic energy? Yeah, temperature is basically a measure of your average kinetic energy. So does that equation have molar mass in it? No. So does your average kinetic energy of your sample matter about what gas it is? No, it doesn't. So that one does not depend on the identity. Do we see that? But then what is dependent does the speed change? Does the speed change of your sample? Yes, it does. So your average kinetic energy doesn't change if you change the sample, as long as the temperature stays the same. But if you change your sample, the individual speeds do change. All right, okay. Rate of which a gas molecule collides with container walls. So that kind of gives it away. Since I said velocity changes, D also will change based upon your sample. Rate of a fusion through a pinhole. Yeah, it does depend, because if we use Graham's law, remember we use molar mass over molar mass, that equation. So again, depends on the identity, so that one's wrong. Oh, this isn't a select all. Sorry, I thought it was a select all question. So we would have stopped right at C. Okay, good? All right, yeah, so the fallback here is look at your equations and interpret what that means. For me, how I interpret it is identity of a gas. That depends on if molar mass shows up in the equation, then it does depend on the identity of your gas. And so looking through all of these, C, your average kinetic energy is the only one that doesn't. Okay, all right, which is not a part of kinetic molecular theory? So 1, kinetic molecular theory explains what type of substances, what chapter did we learn about it? Gases, yeah. So it's why the ideal gas law works. It's why those named gas laws work. Okay, so not part of kinetic molecular theory. Atoms are neither created nor destroyed by chemical reactions. Okay, to me, that one is the right answer, because it's not specific to gases, right? So let's just read through them. I want to make sure that I'm right. Okay, B, attractive and repulsive forces between gas molecules are negligible. That's true, especially true for the ideal gas law. That's one of the tenets that kind of shuts down when we get to real gases. Okay, all right. Gases consist of large molecules that are in continuous random motion. Yes, that's tenet number 1 of KMT. Energy transferred between molecules does not change, meaning they're elastic collisions. That's true as well. And then E, combined volume of all molecules of gas is negligible relative to volume of gases. Yeah, so E is correct too. It's part of KMT. B through E, they all describe gases. A is the only one that doesn't describe gases. It's actually like Dalton's, his billiard ball model type thing. Okay, all right, let's keep going. Oh, okay, MOs. look at these MOs. Which of the answers is correct? So all of these pictures are depicting molecular orbital combinations. So we typically, when we combine two different atomic orbitals, we get two molecular orbitals back, right? Okay, so, but here we see kind of a depiction of only one of those MOs that come out. So we are trying to say, okay, in A, this molecular orbital is made from the combination of two p orbitals, that this is sigma bonding, or sigma a bonding orbital. What part of that is false? The sigma, right? So is A the combination of two p orbitals? Or is it, so I'm just going through each sentence. Is it the combination of two p orbitals? Yes, it is. So that part is correct. Do you see the two p orbitals where they came from? It's like a dumbbell this way and a dumbbell that way. They're coming together. But when you combine them and make your MO, they just redistribute a little bit. So you still see reminiscent of what a p orbital looks like there. Okay, so that part is true, but the sigma and the bonding are not true. It really should be sigma star. You see that? Because the bonding is away from the atoms. These black dots, those are the atoms themselves. All right. Okay. Here is another type of orbital. I won't tell you what it is, but it's the combination of four p orbitals. It is pi bonding. It's a pi MO, and it's anti-bonding. Yeah, so this 4 number is not correct. Right? So I think what they're trying to do is get you to think, oh, there's 4 lobes. Yeah, it's not. This is the combination of 2 different p orbitals. Is it in a sigma fashion or a pi fashion? Pi, yeah. So this part is correct. Is it anti-bonding? Yeah, so it would be pi star. Okay. All right, let's keep going. All right, C. Combining 2 s orbitals, sigma bonding. No, yeah, they're p orbitals instead. Is the rest correct? Yes, it is correct. So this is actually sigma between 2 pi orbitals. Okay. All right. These are the combination of 2 p orbitals. It's pi. It's bonding. That one's the correct one. Yes. Yes, we see it. Okay. Let's just make sure E. Let's make it correct. Combination of 2 p orbitals. Sigma. It's bonding. It's s orbitals. Very good. Cool. There we go. All right. All right, so let's keep going. All right, so which of the following ranks the bonds from nonpolar to ionic? The most nonpolar to ionic. So if you kind of just write them all out, we have KCl, we have CO2, we have S8, and then we have BF3. So if you have your periodic table, it's going to help. It's going to help. I always like to identify the ends. The ends. So of these, I feel like straight away you can find the nonpolar covalent, which is going to be S8. Yeah, this one's completely nonpolar. It's all the same atom. So when you calculate delta En, it has to be 0. Yeah. Versus which one's going to be the most electronegative, therefore, the most delta En difference. So you have a really high ionic. Yes, KCl. So this one is ionic. So it is A or C, I think. Those are the ones we've eliminated. And so it's the middle ones that are weird, CO2 and BF3. So I just locate those on the periodic table. And so you see boron is over here, fluorine's over here, carbon, oxygen. So when you calculate delta En, which one, since electronegativity increases left to right, the largest difference you're going to get is going to be between boron and fluorine. Do you see that? Yeah, okay. So then that means BF will be next. So the answer, I think, is A. Did I get that on my thing? Did I? Okay, good. All right. Okay, we only have a little bit of time left. Is there a certain chapter? Chapter 9, what was that? Oh, okay, here. Then let's just do this one. What are the hybrid orbitals, the hybridization of nitrogen, sulfur, and the singly bonded oxygen in this atom? I feel like this is a nice giveaway question. Hybridization, because hybridization of an atom comes from the number of electron domains. And that is something, especially if you're already given a Lewis structure, you can just count. Yeah. It says the singly bonded oxygen. Oh, yeah, so, no, like has single bonds. Yeah, okay, all right, yeah. So I just count. So nitrogen has 1, 2, 3, 4. So is it hybridization 4? No, it's SP3. Meaning 4 comes from, so how do we go from 4 to SP3? Wait, what? Okay, so, okay, yes, number of electron domains gives us the geometry. But remember, the number of electron domains tells us how many atomic orbitals to combine. So if it's 4, we need S, P, another P, and another P. So it's SP3. Versus the next, so that's SP3, that sulfur, it only has 3 electron domains. All right. So yeah, it's SP2. So we combined an S, a P, and another P. We only need to combine 3 atomic orbitals. And then the last oxygen has how many electron domains? 4. So then our answer, I think, is D? Is it D? Yeah, it's D. Yeah, okay, all right. All right, so let's talk through this one. Question 15. Removal of an electron from oxygen blanks the bond. Removal of an electron from N2 blanks the bond. So what is this referring to? Bonding, yeah, so we're adding or removing electrons from either bonding or anti-bonding orbitals. So can I just like me personally, I can't just look at this and know the answer. I need to draw what? The MO diagram for oxygen and nitrogen. But remember, you're given that, or you're given the template. You just need to know how to use it. So oxygen is, if I just draw the P interactions, oxygen goes, crap, I actually forget what it is. Wait, no, it's the other way. It's this way. Okay, so it goes sigma, pi star, and then sigma star. While nitrogen, it has sp mixing, so it goes 2, 1, 2, 1. So this is pi, sigma, pi star, sigma star. Of course, you're given the orders, and it will straight up tell you, like, this one's for oxygen, this one's for nitrogen. I don't have it in front of me. And so then you just place the correct number of electrons in there. So oxygen has 2 electrons in antibonding. So when you do 6 minus 2 over 2, you get a bond order of 2. And then nitrogen is just like that. And so we're removing an electron. So you can just calculate bond order if you make the cation, but I like to think, okay, if you remove an electron from O2, you're removing an electron from antibonding, so you strengthen it. Right, so yeah, the bond order goes up in this case for oxygen, and then for nitrogen, when you remove an electron, you're removing it from a bonding orbital, so your bond order goes down. So this should be thinking about weakens or strengthens. Your bond in O2 is what, strengthening or weakening? Strengthening. And then for nitrogen, it will be weakened. So the answer is D. But what if instead of weakens and strengthens, what if it said made shorter or longer? Then it would be the opposite. Yeah, but we still do the exact same process, right? You look at bond order, we're just looking at a different trend. Okay, a billion ways to ask the same question. All right. So, okay. Here's another one, and I kind of like open it for you. Based upon MO theory, the bond order of O2 2 minus is blank, and the species is blank. So again, this is building the MO diagram, all right? What is an MO diagram? Molecular orbital. Like, what makes it different from atomic orbitals? I don't know. Okay, the whole idea is, okay, how do we go from like atomic orbitals on an oxygen atom, like we have p orbitals, right? It's 2s2, 2p4, whatever. So we have two oxygen atoms all hanging out by themselves, but when we think about oxygen, it exists as O2. So do recall from chapter 6, when we talked about these orbitals, when I say an orbital, it has a shape. That shape actually comes from solving the Schrodinger equation, right? And getting your quantum numbers. Those quantum numbers tells us the probability of finding an electron. So it's the whole idea that electrons are waves. What is that? I just noticed that, got scared. Electrons are waves. So what you're seeing when you look at a contour plot, for an s orbital, like it's a circle, a p orbital is a dumbbell, you're looking at the wave function, the contour plot of finding an electron on that atom. So these are atomic orbitals. When we think about molecular orbitals and we do the combination, we're treating electrons as waves again. And so when we take the wave functions from the atoms, when we combine waves of two different atoms together, we get molecular orbitals. And so we're looking at how do those interactions happen. When we combine two wave functions of atoms, we get two wave functions out for a molecule, essentially. So that's why it's the whole idea is the number you get in is the number you get out. It's kind of the basis of linear combinations here of atomic wave functions. And so that's what we do. When we draw these lines, when we draw the lines here for MOs versus atoms, atomic orbitals, we're actually describing a wave function. Okay, so that's relating it all the way back to chapter 6. And it's the reason why we know what an s orbital looks like. We know what a p orbital looks like. It's because that's the solution to its wave function. Yeah. No, exactly, yeah. So when we combine two s orbitals, we get what orbital MO is down here? S, or not, so we combine two s orbitals, so we get sigma. And then what's the one up here? Sigma star. Yeah, so when we combine two sigma. Yeah, so, or two p orbitals, right? In a sigma fashion, we get one that's stabilized, that's constructive, addition of two waves. And then, bonding, it's the same exact thing, but the way we are interpreting it as chemists is bonding, but how the waves are actually adding together mathematically is constructive interference. So that's your sigma orbital, and then your one up here, that's higher in energy, that's your sigma star. That is your deconstructive interference, that the waves cancel each other out. So it's less stabilizing. So that's the whole idea. So when we draw these things, these MOs, these lines on a page, really what we're doing is we're combining wave functions and we're treating electrons as waves. So that's where this comes from, and that's what ties the whole advanced bonding theories together. But do recognize it's very complex. This is, MO theory is super complex, and as it should be, because we're combining wave functions. Okay, how much time do we have? Not much time. Is there any last question we want to do? Yeah. Oh, these lines? Oh, I knew that, so oxygen, one oxygen atom has how many p orbitals? Or sorry, p electrons, one oxygen atom. P electrons, 4. So since we have 2 oxygens, there's 8. Yeah, so what I didn't draw were the lines on the outside, these ones. So what you really need to do is fill up these ones first. So you'll get, for oxygen, you have 4 electrons, 1, 2, 3, in the P subshell. And so you are just rearranging these 8 electrons total in a new type of geometry. So you have 1, 2, 3, 4, 5, 6, 7, 8. These are just the p electrons. I'm not showing the s electrons because those are filled and I like to ignore them. Yes, and then add 2 more for the 2 minus. So I guess the answer here is has how many, what's the bond order? I think it's 1 because there's 6 in bonding, 4 in anti-bonding divided by 2, and it is diamagnetic, so it's A. I think that's the answer. Cool, yeah. Yeah, I'll still have office hours. Okay, I have 5 minutes, so I wanted to start my spiel. Gross. Okay, so I'm gonna end here. So I wanted to share with you all what you guys wrote for the words that made you think of chemistry. All right, and so I'll post this on our page or whatever. Yeah, so not all of you, read the assignment. I said 1 word. Yes, so I put it all together, and I think we all came to similar conclusions of what we think about chemistry. So I do want to say, I see words like stress, pain, and I think that's okay. I mean, this is a tough course, and, I don't want to say like no pain, no gain, but, chasing your passions, it's not always going to be easy, and as long as you keep rising to the occasion, you'll keep growing from it. And so that's something like me, like 5 years ago, I never thought I would be in a room. Okay, I'd hope there'd be more students than this on the last day, but I never thought I'd be here, and because I always rose to the occasion, I never saw how much growth I was doing along the way, and I really hope your college careers, you can achieve that too. But I think the whole thing out of this is that the big important words, are up there, and some other funny ones, okay? So I thought it was funny, okay. Yeah, I like the Lisa too. Okay, so I wanted to talk about a little bit about chemistry, misconceptions. I kind of brought this up previously at the beginning of the term, and I'm all about breaking stereotypes about what it means to be a chemist. And I hate, this is my pet peeve, chemists, they are always the villain. Media always portrays chemists as villains. So like Breaking Bad, who's watched Breaking Bad? Okay, a couple people. I've never watched it, it's a little too intense for me. But like it's chemistry teacher gone evil, right? Evil drug lord. And I think it's funny, like his nickname is Heisenberg. And so do you remember when we learned about Heisenberg, uncertainty principle? About the whole electron wave particle duality. And he kind of makes that transition between like good guy, bad guy throughout the series. I don't know, I actually never watched it. That's like a reach, but again, chemists gone bad. Or I think more people have watched Wonder Woman, right? Their villain was a chemist who designed like a gas poison that didn't use sulfur, and like they weren't even like unique or creative about. They called her Dr. Poison. Like that's not even creative. Like low effort right there. Okay, so I do not like the whole trope that chemists are evil, and so I don't think I'm evil. I don't want to say what you guys think, but I did come up with one example of a chemist who was not evil, and someone that I think you all know, maybe, or watch this movie, yeah, Big Hero, oh, yeah, see, I get the same response every time. Yeah, so in Big Hero 6, like the whole super team here, Honey Lemon was a chemist, and her whole, like, yeah, she's so cool, and her whole, like special, power was being able to come up with like special chemical weapons on the spot. And I found like this meme thing about her saying like how awesome she is. Like, look at her purse, it has a periodic table on it. She's not just like throwing pre-made balls or whatever at the opponent, she's making them on the spot, okay? But not to ruin it for you. We learned in this class, chemical properties has to do with both composition and structure. So if she has the periodic table on her belt and she can type in the formula, that's only accounting for composition, not structure. So it's not super believable. I'm sorry. All right. Not to destroy a kid's show, but it is still cool and she's really awesome. So, all right. Yeah. So that's it, guys. Yeah, so thanks, guys. Yeah. Sorry for the weird day. Samesies. Okay. All right. Do you guys not know where to go? Okay, if you want to, do you want to stay? I'll talk about my tractor if you want to talk about my tractor. Yeah. Yeah, what's up? Huh? What's what?
How many joined the Zoom?
Oh, I don't know. How many joined the Zoom? I don't know. I don't know how many. We had 60, there were 50. Okay, perfect. All right. So if you want to stay, I'll talk about my tractor here. Okay. So I was going to do a demo. Do you have a question?
Yeah, real quick.
Yeah, what's up?
21.
Yeah.
So there's 5 S and 2 P, right? Does that mean that there's 4 unhybridized P orbitals, or is it still
1, 2. Nope, it's 4.
It's 4 unhybridized P orbitals to make 2 P bonds.
Yeah, actually, this should say sigma and pi.
Yeah.
Not. Yeah,
S and P.
yes, it should actually have the Greek letter. Yes,
But it'd
yeah.
be 4 unhybridized to make 2.
Correct,
Okay.
correct. Because just making 1 P interaction, you need 2
Gotcha.
P unhybridized pieces. Okay, so my tractor. All right, I was going to do this demo, the same one as before, the hydrogen balloon. So you do have hydrogen, oxygen, whatever, to do that. But I had balloons with different ratios of stuff in them. Yeah, and so from this was kind of like a limiting reactant question type of thing, because you see the ratio of hydrogen and oxygen is 2 to 1. And if you have that ratio within your balloon, you're going to get the most chemical conversion. So if we have oxygen, just oxygen, we have no hydrogen. So when I pop the balloon, would it go boom? No, not really. Not really. It'll probably pop, make a little bit of boom, kind of combust things around it, but it's not going to be super big. But then once we add hydrogen and oxygen, now we have both things, but is it in the right ratio? No, yeah, once all of the hydrogen gets consumed, there's still a lot of oxygen left over. So you're not getting as much conversion. So H2 is a limiting reactant. So you're running out of fuel, essentially, here. And I was going to relate it to my tractor. It's about, we call it running lean on your carburetor, where you don't have enough fuel going into your engine, but too much oxygen coming in. So you're what they call running lean, and you have to, and I was going to show the carburetor, all right, 2-stroke engine. You can adjust your carburetor to change the fuel-air mixture. And so the whole point of doing that is to get the best ratio of combustion. So, well, once we go 1 to 1, are we still at the optimum mixture? No, we're not. So when we do the popping, it'll still go boom, but it's not. So what Angie told me how this does, she says it goes pop, boom, boom, then huge boom, and then something else happens. So yeah, so in this one, it still goes boom a little bit, but not as much. But then this one where we have twice as much hydrogen and 1 equivalence, yet this is the correct ratio. So this would be the loudest boom, because we have basically every particle of H2 can react with every particle of O2 in that balloon to give us the most energy conversion, because it's in a 2 to 1 ratio, all right? And so this would be like in your carburetor having the right air fuel mixture, where you're converting the most fuel possible given the amount of air there. But then this is, what if we made it all H2? What if we just made all of it the fuel source? No oxygen. Yeah, and so a lot of people will think, oh yeah, you add more fuel, you'll have a bigger boom, but that's not how it works. Even if you mess up the ratio in your carburetor, you can what's called run rich, and your engine doesn't work very well either. In that case, when you run rich, you have way too much fuel, not enough oxygen, so you get incomplete combustion. So in this case, where we just have hydrogen, a lot of students, they will incorrectly think, oh yeah, that's going to be the biggest explosion, but it's not. It's actually slightly smaller. Remember, we live and breathe in oxygen, so it still explodes because there's oxygen around it, but not as much as the previous one. And so that was the demo I was going to do, but didn't. So there it is. H2, let's go back to the equation. It's not H2O liquid, it's gas. Yeah, so it's a vapor. Yeah. So that was it. That was me talking about my thing. That's it. Oh, because we couldn't do demos because there's like the sprinklers don't work, the eye wash station doesn't work. Yeah, we want to be like super safe. Sorry. And I probably still wouldn't do it for that reason. Because what if there was an emergency and like we didn't have water? Yeah, that sucks. No, I know. You just imagine, okay? You can just imagine. It's a little boom. Okay, so it's like little. It's actually, no, I think this one's just like a pop. I've actually never seen it. I'm just assuming. It's pop, boom. Okay, like boom. And then like boom. And then like boom. Something like that. That's what would happen. So close your eyes and imagine it. What? Yeah, because you need oxygen. So yeah, we live in oxygen. So there'd be, yeah, a little bit, probably. I'm assuming. That's just my I have no idea. I've never done it, and I would have done it here, but I didn't. Yeah, I do hope so, unless this happens again.